show you the company that I'm working for. Second, I will explain you the project that I'm working in. I'll show you the design workflow that we follow with the model-based design. Also, the motor technology will be explained. We'll show you how we integrate the MATLAB tools into our workflow. And finally, we'll show you the results. So French Powertrain is a Belgian company. We are headquartered in Sint-Truiden. We also have an R&D office in Eindhoven. We have a small after-sales office in Malaysia and an assembly plant in China. We are an independent supplier of clean powertrains. It all started with DAF. That's the car you can see one floor lower at the staircase. That's one produced by DAF in 1972, which is when our company was founded. Then we had a really difficult situation. We always had one customer in Europe for the CVT transmission, and due to that we had a different owners because they didn't really believe in the company. In 2006, we became French Powertrain, and the current CEO, he focused on the Chinese market. And at that time, all the Chinese people, they started buying their first car. And you may know whether or not, but they're with a lot of people. So it's a really booming market. And from then on, the growth was really incredible. So when we started, we produced 30,000 transmissions per year. Now, 10 years later, we make 30,000 transmissions per month. We also have now more than one product, and I will explain that later. And the growth you can also see with the number of employees. Just after the crisis in 2009, we were with 130 people. This year, we'll hope to land with 700 people. But for that, we still need to fill 66 vacancies. So if any of you is looking for a new job, just come to me after the presentation, and I'll give you a new job. If you're good enough. For 2020, we want to end up with 1,200 employees. So that's also with the number of employees, the tenfold within 10 years. The automotive landscape has many different powertrains, ranging from fully conventional We also develop electric hybrids that can be used from mild hybrid to a range extent. Currently, we have an application for that, so that's the design customer to go into production for the plug-in hybrids. Our electric drives, they can be used in an electric vehicle, of course, but if you use them in a through-the-road concept, they can also be used in a full hybrid car. For the electric powertrains, we have a single-speed transmission, we also have a twin-speed transmission, and we even have a transmission where you can use two motors and combine them in one single-speed transmission. We also do some research on liner-based transmissions. That's to be cost-effective because the batteries are still very expensive, and if you can store the energy in mechanical speed, that's more cost-effective than a battery. Now I would like to show you the project from which I will be presenting the results today. It's a European Union-funded project called ARMEVA that stands for Advanced Relentless Motors for Electric Vehicle Applications. It has partners from all over Europe, and we've been working together quite intensively. And the goal of the project is to develop a new generation of burn-free electric motors, because it means no minus, based on magnetic reluctance. The content of this project is to develop a complete drive system. That means a motor, power electronics, and controls. To be competitive in the future, the focus lies on an increase in power density and an increase in efficiency. And to reduce the cost, we integrated the motor and the power electronics within the transmission. In the past, we had a transmission, we put a motor to it, and then next to that, we had a casing for the power electronics. In this project, we integrated everything into one package. Now, why would the European Union be interested in funding a project like this? Well, that is because with the outcome of this project, we can build electric cars at a lower cost with an increased efficiency. You may know a famous Californian company producing EV cars. Well, I see the gentleman smiling. It's like a high-end iPhone on wheels. It's not yet affordable for everyone. What we try to do is build Android on wheels, so the OEMs can integrate our systems into more affordable cars. And that will lead to more electric vehicles, which is good for everybody. Now, developing an electric powertrain, how do you start on it? Well, this is the design workflow that we've used for this project. First of all, we start with the vehicle requirements. For that, we built a high-level model. That model can be further refined to determine the e-drive requirements. And the step after that was that we simulated 3 different motor types to determine the best one. These motor models were used to do the electromagnetic design, but also to help the other partners to design within their own domain. One example is that we have simulated the main cost drivers of the final product. And for that we did a sensitivity analysis of the switching frequency. So we used the model of the complete system to determine how low we could go with switching frequency that results in cheaper IGBTs. So we have designed 3 different reluctance motors. A reluctance motor is part of the family of the synchronous machines. And these 3 motors were designed by 3 different partners in the project. In the end, the 3 models had to come together because when we were building a prototype, we only wanted to build one. It would not be feasible to build prototypes in cars with the 3 types. In comparison, we did based on cost, efficiency over drive cycle, and noise. So to be able to do a fair comparison, we needed the simulation models in quite a high detail. Because for the cost, you need to know all the components, the cycling of all the components, so as well as mechanical and electrical. To be able to calculate the efficiency over drive cycle, you need to know the losses in detail of the different motors, and that you can apply back to your vehicle model. But for the noise and the vibrations, you need to simulate the forces that result from the control strategies and mechanical design. In the end, it was a switch reluctance motor that had the highest overall score. Is there anybody in the room that knows how a switch reluctance motor works? One guy. So a switch reluctance motor is characterized by its double salient structure. That means it has discrete rotor poles and stator poles. It's driven by a reluctance torque. What that is, you can compare to an electromagnet. So if you energize the coils of the stator, you generate a magnetic field. And the torque is then produced by the tendency of the rotor to move towards the position where you have the smallest air gap. All the benefits from this motor result from the fact that the rotor is just a simple block of lamination steel. The high-speed capabilities, the robust construction, the low cost. Now you might think, why is not everybody using a friction reference motor now? Well, that's because due to the physical properties, it has quite a high torque ripple, and also the noise that it generates is really not pleasant if you don't counter it. If you have to solve these problems, with really high non-linear behavior of the motor, you get quite a challenging job in designing the controls and the power electronics for the motor. The sound you just heard is from the first generation of these motors. You might be able to stand it for 10 seconds, but if you're on the highway, you really don't want this in your earplug all the time. I would love to show you also the sound that the Arriva motor produces, but it's so bright it wouldn't make any sense to show it here. Next, I would like to translate these challenges that are inherited from an SR motor and apply them to the challenge we have within this project. Within this project, we decided to double the maximum speed up to 20,000 RPM. That means we have less time to put the current in the coil within the optimal time frame, and to counter that, we have to reduce the inductance. In the end, we ended up with an inductance that leads to a current rise time of 8,000 amps per millisecond. That means that in your software or your hardware, if you have a delay of 1 microsecond, you already get an error of 8 amps. In the previous designs, we always used the processor, and even with the simplest control strategy, so normal piece readers control, you just measure the current. If it goes above a certain limit, you switch to IGBT. That simple piece of software already takes 14 microseconds. If we would use that in the Arriva motor, we would get an error of more than 100 amps, which is just not usable since the maximum current rating is 450 amps. And that was not the only challenge we had in Arriva. We also wanted to use new innovative control strategies like direct current control, and there within one time step, you have to take the current in one phase, combine it with the position of the rotor, do that in a lookup table, and you get the torque that phase is producing. That you have to do 3 times in parallel for the 3 different phases, and then calculate the optimal switching strategy. Now, I don't know if everybody completely understood what I just tried to explain, but I think you can imagine it's just not going to work if we would use that processor from the past. Therefore, we decided to use an SoC device. That's a processor that's glued together with an FPGA. We're choosing the Zing device, and that leaves us one more challenge. We have nobody in Punch that can program an FPGA, but that's only not on the software store. Stefan explained to you just before the break how does the workflow works to generate code for the FPGA and the processor. The principle is you just design your control strategies with a model, and the part of the processor